Assalamu alaikum and good day. For today, we are going to continue with our lecture. This would be our last topic for this semester, and it would be heat exchangers. Now, so later on in your fourth year, third year and fourth year, you're going to have design IDP and also design project. So the heart of the design project would be heat exchangers, where this would be the equipment that used to facilitate heat exchange between two fluids that at different temperature and separated by a solid wall. So heat exchangers are quite important since in the plant, in a chemical or earlier chemical plant, we rely on the uh, hot fluid to give or to transfer energy to the cooler fluid. So this lecture aims to introduce performance parameters for assessing the efficacy of heat exchanger, and also it also develop methodologies for designing a heat exchanger under prescribed condition. Now, there are several usage of heat exchanger. The first one is to transfer fluid from one fluid to another, to transfer energy from one fluid to another, and also to get the fluid stream to the right temperature for the next process. For example, if we wanted to have the feed stop for our reactor to be at 50 degrees centigrade, we usually would need a heat exchanger to heat up that feedstock to 50 degrees centigrade. And also to condense vapors, so we have condensers, and also to evaporate liquids. The next usage would be to recover heat to use elsewhere. For example, energy recovery. In top glove plants or top glove factories, they are using hot wastewater to help to heat up the fluid stream. So in a way, they are using the existing energy to or to use the heat, they recover the heat that uh, produce in a certain equipment and use it to heat up some fluid stream. So the examples that we use heat exchangers are space heating, refrigeration, air condition, power plants, chemical plants, petrochemical plants, petroleum refineries, and so on. So these are the usage for heat exchangers. And in order for us to characterize the heat exchanger, we can characterize it into flow arrangement or type of construction. So there, if we wanted to characterize it to its constructions, there are actually three main types of heat exchanger. The first one would be concentric tube heat exchanger. So what does it mean by concentric? So meaning that we have a pipe, and then we're going to have another outer pipe. So in a way, they are concentric. So it might be in the parallel flow or it might be in the cross flow, but usually we have cross flow. So for example, if we wanted to increase the temperature inside of the cylinder or inside of the pipe, so this one T1 and T2, so it might be T1 is more than T2 or T2 more than T1. So it depends on the usage, on the situation. And the second one would be Sherland tube heat exchanger. So what does Sherland tube means? It means like you're going to have a shell, a big shell. Maybe we can use carbon steel. So what happens is that you're going to have inlet. So this is two pass. So you're going to have like so this is going something like this. So the flow would be like this is the flow in the shell, and then you're going to have tubes. So this would be the tubes inside. So this is not good. So so it would be like this. So this is shell and tube. This is shell and this is tube. These are the tubes. And also another one would be compact heat exchangers. So compact heat exchangers are used due to the fact that if that factory of that installation have a limited space. So usually we use compact heat exchangers on an oil and gas platform. Right, so in order for us to select heat exchangers, there are several criteria, and the first one would be the operating pressure and temperature. So if we have a very high operating pressure and temperatures, usually uh, uh, we will not use a concentric heat exchanger. And also the folding characteristic of the fluid, whether it's tendency to fold due to temperature or suspended solid is higher or not. So it will affect our uh, selection of heat exchangers, and it also the available utilities. So whether we have cooling tower, water, or steam or hot oil, and also the size, whether we have a very big uh, what what size do we need for the heat exchangers, and also the accessibility for cleaning and maintenance. So as you can see that Sherland tube needs to have cleaning and maintenance, and also consideration for future expansion, mechanical considerations such as material of construction, thermal stresses, impeachment protection, and the end would be cost. So if we refer back to the types of heat exchanger, as we move downward, the cost would be higher or increase. So the cheapest one would be Concentric, followed by Sherland tube, and the most expensive one would be compact heat exchangers. So that's why usually we only use compact heat exchangers on an oil and gas platform offshore. Now, so this would be the principle of concentric tube heat exchanger. So we have two types of flow. We can have parallel flow. So parallel flow if both the inside and also the outside liquid flow at the same direction. So this is parallel flow. And we also have counter flow. So counter flow if let's say the inside fluid and also the outside fluid are moving in the opposite direction, so we call it as counterflow. The first advantages for concentric tube exchanger would be it would be the simplest configuration, and if we use counterflow, we're going to have a higher performance or efficiency, and also it's cheap for both design and maintenance, so it's a good choice for small industries. Therefore, if you go to small oil palm mill, they usually use concentric tube heat exchanger, uh, but I think they're going to phase out the concentric tube exchanger soon. But the disadvantage would be its low efficiency, and in order for us to have a higher efficiency, it would be we would need a counterflow, but it's still not up to the standard of Sherland tube heat exchanger, and also the high space occupied. So I'm going to show you an example of concentric tube heat exchanger, an example of tube heat exchanger. So this is a bundle of tube heat exchanger. So instead only or having only two passes, they have like 1, 2, 3, 4, 5, 6, 7, 8 pass. So 8 pass concentric uh, passes. uh, concentric tube exchangers, and this is very tall. If let's say normal person stand next to it, this would be a normal person, that person, so it would be very large. Similarly to these two pass heat exchanger, so let's say that you are sitting here, standing here, it would be something like this. So this is quite large, so that's why the space occupied are very quite big. And these two would be an example of counter current of cross flow. So this is also cross flow heat exchanger, and this would be a parallel flow heat exchanger. Okay, so next we are going to see the Sherland tubes heat exchanger. This is a bit lengthy. The reason why we focus on Sherland tubes heat exchangers is that most of the time in oleochemical industry we use Sherland tube heat exchanger to heat up fluid. So for example, if we have something like this would be an example of shell and tube heat exchanger. So we have shell inlet, and also this is a single pass, meaning that the shell, the fluid in the shell inlet only pass through that uh, particular shell in one direction. So that's why we call it a shell, one pass, single pass. And also we're going to have a tube inlet here. So this going inside, going outside. The fluid will not mix together. So it would be at different, not location, but different orifice. And uh, it can be fabricated from a wide range of materials, depending on that particular liquid or fluids corrosiveness, and also uh, characteristic. And its design is more rugged than other types of heat exchanger and can stand extreme process condition. So you're going to see, most of the time you're going to see shell and tubes in industry. And the design pressure range from full vacuum to 6,000 psi, and design temperature ranging from negative 250 degrees centigrade to Celsius to 800 degrees Celsius. So it may not be the most economical or most efficient selection for heat recovery application for highly viscous. The reason why, because as you can see, we have tubes here. So if we have a very viscous fluid, the tendency of the viscous fluid to fall inside of the heat exchanger would be higher. So we will need more time, more maintenance, and also more cleaning time. So that's why it's not really a good selection for highly viscous fluid. And the typical application would be condensers, reboilers, and process heaters, coolers. So these uh, three applications are actually inside an existing equipment. So for example, condenser and reboiler, usually we put in a distillation column. So it doesn't mean usually it's not a standalone um, equipment. We are going to embed this shell and tube heat exchanger inside an existing equipment. So this would be an example of shell and tube heat exchanger. So if we refer to the first figure here, we will see that, for example, if we have uh, this would be the inlet of the shell tube. So the hot side here shows shell inlet. So the shell inlet here will move through the outside of the tubes, and it will go straight to the shell outlet. So as you can see, it will move something like this due to the baffle and so on. Okay, so this would be for shell side. So for tube side, this would be the inlet of the tube side, tube inlet. And the tube, for example, if we only focus on a single tube, so we have a bundle of tube here, so focus on one single tube. So this tube here will not mix with the liquid in the shell side, so it will move in a tube, in a single tube, and it will come out here. So this would be the tube side outlet. Why do we have baffles here? This we call as baffle. Baffle is to ensure that the movement inside the shell side is in turbulence, because as you can see that from previous lectures, if we have a turbulent flow, the heat exchange, the rate of heat exchange is much higher. So that's why we wanted to make it turbulence. So this would be the tube inlet and tube outlet, shell inlet and shell outlet for shell and tube heat exchanger. So this would be an example of a clearer example of shell and tube heat exchanger. However, here we only have single pass for this is, so as you can see, if we have baffles here, something like this, so it will, it's not good. So I need to, okay, so I need to erase this part. Okay, so let's say that we have a single pass. So this is a single pass and we have going to have baffle. So it would go something like this. And this is for the shell side. So this would be, as you can see, we only have a single pass shell side. And also for the tube side, we only have one single pass also. So in a way, we call it as a single pass heat and tube shell heat exchanger. Now, why we call it shell and tube heat exchanger? The reason why, because it's named for its two major components, which is the round tube mounted inside a cylindrical shell, and the shell cylinders can be fabricated from roll plate or piping. But the piping, if only the diameter of that shell is less than 24 inch. So if it's more than 24 inch, we cannot find the perfect or the suitable piping. So we have to fabricate it from a roll plate. So we are going to fabricate it from something like this. This is a single plate, and then we're going to roll it into a shell. So this, but it's only if the diameter is more than 24 inch. And other components include the channel. So the channel would be, for example, if we have something like this would be the heat exchanger. So this would be our shell, and this would be our channel. So this is channel, and also we're going to have tube sheet. So tube sheet here, baffles, as you can see previously. So this is baffles. Tyre rods, I'm going to show you later on. We cannot really show it you here. uh, and spacers, plus partition plates and expansion joints. So I'm going to show you later on with the pictures. And the shell tube heat exchanger design and construction are governed by TIMA and ASME code. TIMA is, if I'm not mistaken, is the American codes for heat exchanger, Thermal Exchange Manufacturing Association, and ASME would be the American Standards of Mechanical Engineers Code. So we have two codes that govern the construction of Sherland tube. So this would be the inside of Sherland tube. So first we have nozzle. So nozzle here. So this would be an example for heat exchanger, the inside of exchanger. So we have nozzles here. So nozzle for inlet and outlet, and also we have front channel. This is front channel. This is back channel or rear channel, and also we have support. Support you usually use only carbon steel because this carbon steel would be the cheapest one with uh, quite good integrity, so we usually use carbon steel at the supports. And also we have expansion joint. Why do we have expansion joint? Expansion joint usually use if, let's say, we have different value of the expansion, the thermal expansion parameter alpha, so sorry, beta. So expansion joint, if we have a different value of the expansion, or for example if we have different value of the density when that particular fluid is in liquid form and when it's in uh, gas form. So this would be the shell. And for the tube part, as you can see here, this would be the Tyre Rod and Spacer. I'm going to talk about what the usage of this particular parts. So this would be the baffles, uh, and this would be the tube sheet at the end, at the rear of the baffles. So tubes, the normal tube diameter are usually 5/8 inch, 3/4 inch, and also 1 inch. So this would be the normal tube diameter for Sherland tube. And tubes of smaller diameter can be used, but they are more difficult to clean mechanically. So if, for example, if this is a tube, so it would be very long. In order for us to clean it, we are going to use pipe cleaner. So pipe cleaner is a bit similar to those that we use for normal pipe. So this it would be like something like this. So this would be pipe cleaner. So we'll insert this pipe cleaner and just clean inside of this pipe. So this is a bit um, would be quite hard if we have a very small tube diameter. And tubes of larger diameter are sometimes used either to facilitate mechanical cleaning or to achieve lower pressure drop. Because if we have a very high pressure drop, what happens is that we the thickness of that particular shell or tube would be higher. So usually we wanted to have a lower pressure drop. And also the tube wall thickness range from 2.8 millimeters to 1.7 millimeters, and this would be due to the pressure drop. So if you have a very high pressure drop, you're going to have a higher thickness. And tubing may be thin. For example, inside of this you might make it corrugated or thin, or you have something like this. So if you have thin inside of the tube, uh, this is corrugated corro sorry so the corrugated surface and also thin surface in order to increase the heat transfer rate due to increasing surface. So it can be done outside of the tube and also inside of the tube. High flux tubes are tubing with special surface to enhance heat transfer on either or both sides of the tube wall. So this is the corrugated tubing. And inserts such as twist tapes can be installed inside tubes to improve heat transfer, especially when handling fluid, viscous fluid in laminar flow condition. This one I think we have, I've shown you before, where we have actually, uh, if you remember that we have a vertical tube moving from bottom to the top, and there's corrugated tube. So if you have a corrugated tube, what happens is that the turbulence inside of the tube will increase and you have turbulence flow. Now, tube sheet, if you refer back to this particular image, this would be the tube sheet at the end. So we have here tube sheet here and also here. So we have at the both ends. So it's plates of forging drilled to provide holes through which tubes are inserted, so it would be secured to the tube sheet. So if we have tube sheet here, we have plates. So these plates are actually drilled. So we have something like this. So it drills to provide holes. So we insert the tubes so it can hold the tubes. So for example, this is not a really good drawing. So actually it hold the tube. And the distance between the center of the tube hole we call as the tube pitch. So if let's say that we wanted to see this particular, so we enlarge it. So this would be the distance between the center of the tube hole. So this is between, if you have two tube hole, and this we call as tube pitch, and this would be the diameter of the tube. So the tube pitch is usually 1.5 times times the outside diameter of the tube, and triangular pitch is the most often applied because of the higher heat transfer and compactness, and also if you remember that it also enhances the turbulency of that particular flow. So this is a triangular pitch. And square pitch facilitates the mechanical cleaning outside of the tube. So this is an example of a square tube. Two tube sheets are required except for U-tube bundle. So this would be two U-tubes at the front and also the rear. So this is front and this is the rear side. And the tubes are inserted through the holes in the tube sheet and held firmly in place either by welding or mechanical or hydraulic expansion. So we have three types of securing the tubes to the tube sheet. So this would be an example of tube sheet. So this would be at the front. If we have look at the front, so this would be the tubes before we weld it onto the tube sheet. So after you have welded, you push it inside and you weld it. So this would be the tube sheet welded onto the tube that welded onto the tube sheet. Um, so we also have baffles. So baffles, this is baffles. So this is baffles. So baffles serve three functions. The first one is to support the tube, and the second one is to maintain the tube spacing. So if you look closely, you will see that the baffle actually have holes drilled onto it, and it held the tube securely. It's a bit similar to tube sheet, but instead tube sheet would be here, but for baffle it would be uh, but in this case we only have, this is not tube sheet, since this is a U-shaped tube, so that we only have one tube sheet here. So this would be a baffle. So baffle will support or held the tubes onto its position, and the second function would be to maintain the tube spacing. So we have spacing of the tubes. It's a bit similar to the first one, so it held the tubes firmly. And the third one would be to direct the flow of the tube. So for example, if we have shell inlet here, if we have a baffle here, it will actually direct the flow of the fluid inside of the shell side. So a segment that we call as baffle cut is cut away. So this is baffle cut. So for example, if let's say that we have a perfect cylinder, perfect circle, and we cut the top one, and this we drill some holes in it. So this is how we manufactured baffles. So if we cut a segment to allow or to permit the fluid to flow parallel to the tube axis, so this segmental cut we call as baffle cut. So baffle cut is here, this part here. It actually it has the characteristic where the height of the segment is approximately around 25% of the shell diameter, which is normally the optimum. So it should be around here lah. Should be around there. And the baffle cuts larger or smaller than the optimum typical result in poorly distributed shell side flow with large eddies that zone behind the baffles and pressure drop higher than expected. So let's say that we have a very big baffle cut. What happened is that we're going to have eddy here. So that zone here, color, if we have a very big baffle, so if let's say the baffle is quite small, but the baffle cut is very big, therefore this is the baffle cut here. So the flow, it would be flowing something like this. So we're going to have a dead eddy here, that not dead eddy, but dead zones, and also dead zones here, large eddies and so on. So that's why we need to ensure that we have a optimum baffle cut. And also the spacing between segmental baffles we call as the baffle pitch. So this would be the baffle pitch. Okay, so there are actually previously we also have seen, if you refer back to this, we also have seen the Tyre Rod and Spacer. So this would be the Tyre Rod and Spacer, and also this Tyre and Rod Spacer are used for two reasons: to hold the baffles assembly together and also to maintain the selected baffle spacing. And the baffles rod are secured at one end to the tube sheet and the other end to the last baffle. So they hold the baffle assembly together. So as you can see, if we refer back to the previous, oops, it's not okay. So if we refer back to the previous image here, the tire and rod. So this is the tire and rod. So this is this part here. It's actually secure the baffles. So this tie and rod, it's actually secure the baffles inside of the shell side, and also it maintain the selected baffle spacing. And the tie rods are secured at one end at the tube sheet and the other end to the last baffle. So they hold the baffle assembly together, and the spacers are placed over the tie rod between each baffle to maintain the selected baffle pitch. So channel or head, so if we refer back to this, so this would be channel, or we can call it head. So channel or head are required for Sherland tube heat exchangers to contain the tube side fluid and to provide the desired flow path. So there are many types of channel available, and the three letters TIMA designation is standard method for identifying the type of channels and the type of Sherland tube heat exchanger. So if you go and Google TIMA designation, there will be three type of heat exchanger. The first letter represents the front channel type, whether the tube side fluid enters the heat exchanger. The second letter represents the shell type, and the last letter represents the rear channel type. I'm going to pause upload a document on the spectrum to see to show you the TIMA designation for Sherland tube heat exchanger. And also we have pass partition. So pass partition is also required, is actually required in channels of heat exchangers with multiple tube passes and direct the tube side fluid through a multiple passes. And the number of tube passes is normally less than 8, and the tube passes allow them to maximize the tube side heat exchanger within the pressure drop. So for example here, we have actually only one shell passes. So shell passes meaning that we only have one direction of the shell passes. So this is the shell pass, a single pass, because we only have one direction. But for the tube pass, we have actually two direction. So this is for the first direction, and the second would be this direction. Well, for so first and second. So we have two passes for tube side. So for shell, for this particular example, we going to have two shell passes. The reason why, because we have two directions. So first this direction, and the second pass would be in the opposite direction. So this would be a two shell pass. For the tube side, we're going to have four tube passes. So first we have this single pass. Second, so you're going to have two passes here, and then inside to the next shell, we're going to have two more passes, tube passes. So we're going to have four tube passes altogether. So the pros and cons of shell and tube exchangers are listed here, where the most the advantage, the first advantage of shell and tube would be it's widely known and it's understood since it's the most common type, and it's most versatile in terms of type of services, and it is the most versatile in terms of types of service, and it also allow a wide range of design pressures and temperatures, unlike the concentric heat exchanger, and this is due to its rugged mechanical construction where it can withstand more extreme condition. However, we also have disadvantage where it's less thermally efficient compared to other types of heat exchanger, and it's subject to flow induced vibration which can lead to equipment failure. So sometimes due to the flow pattern inside of the heat exchanger, we can have vibration. So this vibration, if it's it's very high, the level is very high, we can have equipment failure, and it's not well suited for temperatures cross condition where multiple units in series must be used, and also it contains stagnant zone on the shell side which can lead to corrosion problems. So we have to ensure that the baffle pitch and also the baffle the distance between each baffles is the optimum, and to avoid the dead zone. And we also have to ensure that we don't really use this type of shell and tube exchanger for two phase liquid two phase fluid. Now, so for the next one, we're going to have a look on the compact heat exchanger. So compact heat exchanger are widely used to achieve large heat transfer large heat rates per unit volume, particularly when one or both fluid is a gas, and it's characterized by large heat transfer surface per area per unit volume and small for passages. So there are several types. We have flat frame heat exchangers. I think you are going to see this in your third year LabCom experiments. And we also have heat exchanger, spiral heat exchangers. We can also have flat fin heat exchangers and printed circuit heat exchangers. So as you move down, the cost would be higher. So this would be an example of spiral heat exchanger. So as you can see, this is a bit compact. So we have hot inside this particular space here in the middle, and the cold water or the cold fluid will go from the side. So it will go inside here and move spirally into the heat exchanger and come out here. So the hot fluid will come in the middle, from the middle. So this would be an example of plate and frame heat exchanger. So as you can see that the hot fluid will go inside here, and it will actually the energy will be transferred between the hot and also the cold fluid, where the hot fluid will go interchangeably with the cold fluid in layers. So we have layers between that layers, we're going to have different fluid coming in and coming out. So this would be the layer for hot fluid, and this would be the layer for cold fluid. And this would be a printed circuit heat exchanger. A printed circuit heat exchanger is very expensive, and it's very compact. I'm going to show the video later on, but not in this class. and it's actually it costs for one single equipment, it costs about nearly 2 million ringgit, so which is very expensive for a heat exchanger. However, due to the fact that it's very compact in its space saving, we use printed circuit heat exchanger on offshore platform. So this would be the advantages and disadvantages for pros and cons for compact heat exchangers. So I think you can read it by yourself. However, the advantage for compact heat exchanger would be, first would be this. So this would be the pros of compact heat exchanger, and also would be the area. The area occupied would be very small compared to the other heat exchangers. However, the disadvantage, we are going to have several disadvantage, and the most uh, the most major thing that we need to take into consideration before we use this type of heat exchanger would be the cost, because the cost is very expensive, especially for printed circuit type. However, we still, if let's say you wanted to use pad and frame, it's still okay, it's not that expensive. However, the problem would be it's subject to plugging or falling due to very narrow flow path. So you have to ensure that you clean it every other time. Um, right. So after we have introduced the heat exchangers, we need to do heat analysis to see the performance of that particular heat exchanger. So in order for us to design or to calculate the performance of that particular heat exchanger, we are going to use heat analysis, and the contributing factors include convection and conduction that associated with the two fluids and intermediate solids, as well as the potential use of fins on both sides and the effect of time-dependent surface falling. So this would be the parameters that we take into consideration to do the heat analysis of a heat exchanger. So if we use subscript C and H to designate the cold and hot fluid, we can get the general expression for the heat analysis as this. So the 1 over UA, so this is the overall heat coefficient. U is the overall of that particular heat exchanger is actually equals to this, the summation of all of these parameters. So what are these parameters actually? So if you refer to the next slide, you will see that uh, now not here, now is actually the efficiency of the fin. So if let's say you don't have fin, you're going to substitute now to 1 if no fin. So if you have fin, if you don't have fin, you're going to substitute it to 1, and if you have fin, you're going to substitute to a certain value that correspond to to the efficiency of the fin array. And the second term here and also the third term here actually correspond to the cold side and the hot side, the falling factor. So R double prime is the falling factor. So falling factor of the cold side and falling factor of the hot side. And usually the value of the falling factor, we can get it from this table. So we have two tables here for the falling factors. So we have the first one would be the falling factor, sorry, the first one is for only for the falling factors. The second one is the overall heat transfer coefficient, U. In in the examination or in a question, usually U is given, or you need to get the value of U from the the situation or conditions that given. So RW is actually the wall conductance resistance. So this is the wall conduction resistance. So if let's say that we have a wall here and we have hot fluid, and this would be countercurrent cold fluid. In order for us to get the value of 1 over UA, we need to get the falling factor. If let's say that we don't have the fin here, therefore we're going to have to substitute now not equals to 1, and the falling factor of the cold side, the whole cold fluid side, and also the falling factor of the hot fluid side, and also the RW, the resistance, the conduction resistance of the wall. So this would be the general expression for overall coefficient. There are several methods to calculate the heat exchanger design um, parameters. There are two actually, but however, in this particular subject, we're going to have only two methods. The first one would be the Lmtd method. So I'm going to start with Lmtd method. Lmtd method stands for log mean temperature difference, and it's a form of Newton's law of cooling that may be applied to heat exchanger by using a log mean value of the temperature difference between the two fluids. So this would be the expression of the log mean temperature difference. So this mean temperature difference, the temperature gradient, and it would be represented by the delta T1 minus delta T2 over ln over delta T1 over delta T2. So what is delta T1? So delta T1, if let's say that we draw a graph, something like this. So 1 is the position of the heat exchanger. So for example, if we have this, so this is actually 1, and it doesn't correspond to inlet and outlet. It's actually correspond to the location or the position of that particular inlet or outlet. So it's actually correspond to this picture here. So as you can see, if we try to plot a graph of T versus location of the heat exchanger, we'll get something like this. This is 1 and 2, and this is T. So first we're going to see the hot side. So as you can see, the hot side, since there will be heat transferred to the cold side, we will anticipate that at first at the inlet, the temperature would be higher. However, as the fluid moves in the heat exchanger, the temperature in the hot side will decrease. So it will decrease to a position. So at the outlet, the temperature would be less. So this we call as TH inlet, TH out. So this would be the the direction. And in the cold fluid side, since it's a counter current, so it will start from position 2. So this is X, position 2 of the cold fluid. Since we know that cool fluid will be, the temperature of the cool fluid will be quite low. However, as it moves in the heat exchanger, the temperature would increase due to the energy that transferred from the hot fluid. So the temperature will increase something like this. So this would be the T cold in, and this would be the T cold out. So we're going to have a counter current. So this part here, if we have delta T1, is actually the difference between the temperature of the hot side inlet minus the temperature of the cold side outlet. So this what we call as delta T1. So this is delta T1. And delta T2 is actually the difference of the temperature of the cold outlet, the hot outlet TH0 minus the temperature of the cold stream inlet. So this would be how we get the value of delta T1 and delta T2. So it depends on whether it's a counter flow. So this example, we have counter flow. If let's say we have a parallel flow, we're going to have something like this, and you can try to do the graph yourself, and you will get something like this. And therefore, the value of the delta T1 and delta T2 would be differ from the counter flow heat exchanger. So as you can see that the TC0, or the outlet of the cold fluid, cannot exceed for the outlet for the hot fluid for, so this is this, it cannot really exceed the value of the TH0 for parallel flow. However, if you refer to this, you actually can get the value higher compared to TH0. And also for equivalence value of UA and also inlet temperature, if let's say we have similar value of UA and also inlet temperature, the LMTD or the delta T LMTD for cross flow will be more than the LMTD for parallel flow. So in a way that cross flow would have a higher rate of heat transfer compared to a parallel flow. And for a Sherland tube cross flow heat exchanger, we are going to introduce F, where F here is actually a correction factor, and we can get the value of F from the Levenspiel figure 13.5 to 10. So this would be the correction factor F for heat exchanger, Sherland tube heat exchanger, according to its passes, the tube passes. So this is a single shell pass and 2 tube passes. So the value of F would be depending on the types of Sherland tubes. So it already given here. And for overall energy balance, we are going to have, for example, this is Q. So Q is moving from the hot side to the cold side, and assuming negligible heat transfer between the exchanger and its surroundings. So we are going to assume there is no movement of energy to the surrounding from the heat exchanger, and we assume that's completely insulated, and also negligible potential and kinetic energy changes for each fluid. Therefore, we can get the overall energy balance of each uh, stream as this, where I actually is the fluid enthalpy, and if we assume there is no phase change and constant heat specific, we're going to get this. So this C is actually the heat capacity rate. So for hot side, the value of the rate of heat transfer is actually the same for the hot and also the cold side. For special operating condition, we have several cases. So the first cases, if let's say that we have the temperature of the hot side here is constant, meaning that it's a condensing vapor. So as you can see here, the value of the the cold fluid, the temperature is increasing. However, the temperature of the hot side is constant. So therefore, we will know that the hot side is actually a condensing vapor, and CH would be very, very high. So we can assume that it's approaching infinity. So we can say that it's negligible or no change in TH, meaning that the T inlet and the T outlet for the hot side is the same. And the second case is where we see that for the cold side, the temperature does not change, and this is due to the fact that the cold side is evaporating, and CC, the heat and the heat capacity is C is approaching infinity due to the fact there is no change in TC. So TC here would be the same. And also another one, we're going to have a special case where the heat capacity of the hot side is equals to the heat capacity in the uh, cold side. So we're going to see that the Lmtd is actually the delta T, the delta T1, which is also equals to delta T2. So we have later on, I'm going to show you how to solve the heat exchanger calculation using Lmtd method. But if you refer back to this slide number 32, you will see that this one already been done, so you can try it again. However, for example 2, we are going to do it later on in the class, during the class. So I think that's it for today. I'm going to see you on Wednesday.